Consider a strictly increasing bijective function on the closed interval CD. Since the function is strictly increasing, we know that its inverse must also be strictly increasing. And since it's continuous, we can draw Riemann rectangles for f and its inverse. Let the partitions that define the rectangles be defined by t1 through tn and f inverse t1 through tn. Let's call them p and p prime. Now as the Riemann rectangles get finer, p and p prime become larger sets, and the area more closely follows the exact area cut out by f. The question is, can you prove that the lower sum of f inverse in p and the upper sum of f in p prime add up to BD minus AC? As in, prove that the two areas shaded by the Riemann rectangles represents the area of the yellow area minus BD minus AC. Now, let's go back and properly define what we mean here. We can expand the definition of the lower sum and the upper sum, where mi and mi are defined as follows. Since they are strictly increasing, the inf or min on an interval is a left or bottom endpoint. Similarly for f inverse. Now we can combine them, colors shown here. Since they're indexed by the same sum, we can combine them. The two middle terms cancel out, and we're left with this expression. But now what? Well, I notice we have ti and f inverse of ti minus ti minus 1 times f inverse of ti minus 1. This is actually a telescoping series. With what we know about telescoping series, we can simplify this to the last term minus the initial term. As n goes to infinity, or as the partitions get finer and finer, we have Tn approaching B, f inverse of Tn approaching D, and so on. This approaches BD minus AC. So we can say that as n goes to infinity, the integral of AB of f inverse plus the integral of CD on f is equal exactly to BD minus AC. Rearrange the term, and substitute a and b for f of c and f of d respectively. This is one of our equations. Here's an example using this. Let's say we're trying to integrate the nth root of x on AB. We take our equation, rearrange it, and substitute everything we know about f. This is much easier to integrate. Now the general definite integral of the nth root of x now simplifies to two terms in the integral of y to the n. Taking this expression, simply apply the power rule and we get this expression. Do some algebra. Do some more algebra. Simplify it a bit further, and we get that this is exactly equal to if we just integrated using the power rule initially. But this is a really simple example. You don't need this formula. We can apply this formula to functions that are hard to integrate but have easy to integrate inverses. Can you think of any? Here are some questions to think about. What about discontinuities on f? We see if f has a removable discontinuity, we can easily change the Riemann rectangles to get over that. But if f has a so-called jump discontinuity, f inverse is not even defined on some intervals. Thus, this doesn't work. This is one reason why we differentiate the two different ways that a function could be discontinuous, because they have different properties in some scenarios. And second, where did the telescoping series come from? Where can you find that two terms cancel out in this? If you know, write it in the comments. Thanks for watching.